Thank you very much for your introduction. Carbon footprint has become a very popular concept and is defined as the total set of greenhouse gas emissions caused by an organization, event, product, or person. The main sources are divided in direct or indirect sources. Thus, energy and transport are included as direct sources, while the production of glass, plastic, or any kind of derived products are considered as indirect sources. According to the Kyoto Protocol, it's established a cutting of CO2 emissions, and it's not only established the target, but also the timetable to achieve it. In order to reach this goal, three flexible mechanisms have been proposed in order to get it with the minimum economical cost. These three mechanisms are clean development, joint implementation, and emission trading. Clean development consists on the reduction of emission, while emission trading is a market-based approach that consists on the incentive in order to reduce the pollutant. The carbon footprint is directly related with the per capita consumption expenditure. Thus, according to the maps, it's observed how in the developed countries the carbon footprints vary from 30 to 60 tons of CO2 per year, while in those countries such as African or South American, there are less than 1 ton of CO2 per year. The global aim for the reduction of CO2 has been widely studied for the capture and storage. Nevertheless, carbon dioxide could be used as a chemical feedstock, and this potential application could promote the generation of high added value products and the development of new, efficient, and really challenge new processes. In our research group, we have been focused on the use of carbon dioxide as chemical feedstock for the recycling of polystyrene waste. The global process that we have developed consists on the dissolution of polystyrene wastes, and next, the separation is carried out using CO2. Polystyrene is soluble in aromatic, that the use of this kind of solvents could prevent the further application in food packaging or similar issues. So we propose the use of the pin solvents, particularly in this study, limonene, because they are obtained from the nature, so they are renewable. And also there is an important target that we can observe an important volume reduction during the dissolution. Next, the polymer can be recovered using CO2, since terpene solvents are highly soluble in CO2, but polymers are totally insoluble, so they can obtain again. Also, it's important to stand out that CO2 is inert, non-flammable, nor toxic. It's environmentally accepted, since we are using it as a chemical raw material, and also it's available at relatively low cost. Furthermore, we propose the possibility of recover the terpene oil and the carbon dioxide, but depending on the economical benefit of the global process. The economical benefit of this process would be enhanced if the final product presents a high added value. So, we are focused on the production of microcellular foams from polystyrene wastes. These kind of foams present an average cell size of less than 10 microns and a high cell density, that is around 10^9 cells per cubic centimeter. These microcellular foams present high added value since they exhibit excellent properties that are high impact strength, high toughness, high fatigue life, as well as low thermal conductivity and low dielectric constant. The process for the foaming of polystyrene wastes has been depicted in the slide and is divided in 4 main steps. Initially, the absorption of CO2 in the solution, limonene polystyrene, until saturation of the solution, and next the nucleation of foam bubbles, and finally the growth of those cells. According to this principle, the aim of this work is to determine the range of conditions where the recovery of CO2 to the recycling process of polystyrene wastes provides some economical benefits as well as the reduction of the carbon footprint. In order to achieve this general goal, we have established three partial objectives. Initially, the feasibility of the process from a technical, environmental, and economical point of view has been studied. Next, different scenarios has been assessed. And finally, the economical feasibility of CO2 recycling will be studied. The technical feasibility of the recycling process has been studied from an optimization of the working condition in order to achieve the microcellular foams as we defined before. In the slide, we can observe how the recycled polystyrene presents a very, very small average pore, while the cell's density reaches values higher than 10 to 9 cells per cubic centimeter, and the bulk density is between 20 and 30 times higher than the traditional commercial polystyrene. So we can assure that the process is technically feasible. From an environmental point of view, several management has been studied, several management of polystyrene wastes. The main are the thermal treatment or the pyrolysis, but also it can be added as a raw material. From the comparison of the recycling process that we have proposed for the production of microcellular foams to other traditional management ways, we can assure that recycling of polystyrene wastes allows us the decrease of the resources consumption as well as the demand for landfill space, while we are promoting savings in energy. In order to quantify the emission that we have, that we can promote using the foaming, we have studied CO2, SO2, and NOx. But attending to the CO2, we can assure that from the comparison of the foaming process to the landfill or the pyrolysis of polystyrene wastes, recycling is the most suitable option versus all the management techniques that are traditionally used, since the emission of CO2 are too lower than in the rest of the management. Finally, once that the technical and environmental feasibility of the process has been proved, we have developed the economical assessment of the recycling of polystyrene waste. Initially, we have designed all the equipment in order to evaluate the cost. Once we have studied the cost, we have studied the investment in order to obtain the optimum selling price that has been studied as a function of different scenarios and as a function of the CO2 recovery. Initially, we have studied two different scenarios. The first one is depicted in the slide. It consists on an industrial plant for the production or for the recycling of 9,000 kilos of polystyrene per day. The polystyrene could be collected in different collection points in tanks that contain limonene, that is our solvent. This step, that could be very obvious, allows us the volume reduction that we can obtain through the traditional transport of polystyrene wastes. Next, the solution are fed together with the CO2 to 5 different foaming vessels. 5 vessels are required in order to decrease the dead time and the energy requirements, and also to fulfill the amount of recycled wastes. Once the polymer has been foamed, limonene and CO2 could be recovered to the process in order to study or to determine the economical benefit. Scenario number 2 consists on an semi-industrial or a pilot plant that is able to recycle 100 kilos of polystyrene per day. In this case, only one foaming vessel is necessary, and also the efficiently recycling of CO2 will be studied. Initially, all the equipment were designed and their cost was evaluated. And as we can observe in scenario number 2, where the amount of waste to treat was only 100 kilos per day, there is around 10 times lower of total equipment cost than in the case of scenario 1. Consequently, this effect will be also observed in the investment cost. Investment cost related the fixed capital investment, that is the amount of money that we need for manufacturing and plant facilities, and also the working capital investment, that is the amount of money that we need to operate the plant. So in this case, and following the methodology that is entitled percentage of delivered equipment cost, we have evaluated that in scenario number 2, the investment costs are 10 times lower than in scenario 1. Next, once we have obtained the investment cost, we need to determine the optimum selling price. This price is obtained from the breakpoint. It means that is the point where a business starts to make profit, or is that point where the sales of the product are higher than the cost of the process. So we have evaluated both the optimum selling price in both scenarios and considering CO2 recovery or not. In both figures, and independently of the recovery of CO2 and independently of the scenario, when sales increases, prices decreases. But if we consider the trend market, we have to limit these values according to those shown in the slide. In scenario number 1, we can observe that in those cases where CO2 is not recovered, that belongs to the red line, the minimum sell price should be around 80 euros per kilo. Nevertheless, if CO2 is recovered to the process, this optimum selling price decreased dramatically till reach 3 euros per kilo. This effect is not so easily observed in scenario number 2, where prices are too higher than in the case of scenario number 1. But at this point, I would like to highlight that there is a point in the graph where the CO2 recovery is not beneficial from an economical point of view in those cases where the amount of polystyrene waste is too low. So we can conclude from an economical point of view that CO2 should be recovered only in those processes where the amount of the recycled polystyrene is sufficiently high. Nevertheless, from an environmental point of view, we also should consider that there could be some government aid to promote the recycling of polymers, that also when we are recycling, we don't need to pay for any management costs. And finally, that probably in the future, there will be some bans concerning the use of polystyrene, so we need to recycle this polymer. Finally, I would like to conclude that the decision about CO2 recovery in the recycling process of polystyrene waste is made on the basis of an economical feasibility study, that according to the economical profitability, carbon dioxide should be recovered preferably if the recycling takes part in an industrial plant for the treatment of important amount of waste. That in those scenarios where the amount of recycled waste is not enough to achieve economical benefits of the CO2 recovery, always the environmental impact of its emission must be considered to achieve the beneficial of the process. So thank you very much for your kind for your attention, and if anybody has any doubts.